everyone. My name is Ellie Rosenthal. I am a sophomore electrical engineering student here at the University of Scranton, and today I'm going to talk to you about our Micromouse project that we did. Now, our Micromouse project that we did is where we made a Micromouse robot that we wanted to be able to solve a maze. Now, the maze is a 16 by 16 grid. Each grid is big enough to fit the Micromouse, and the goal here is for the mouse to solve the maze and get to the center in the shortest amount of time. So this competition is actually a very big competition. It is very popular among the engineering community in college. The biggest competition for it that I know of is the IEEE Student Activities Conference, held once a year, where they either give you a robot or you have to make your own robot. So in this case, we had to do the flood fill algorithm, the hardware, so we had to connect the microbit pins to transistors, to the H-bridge circuit, where the H-bridge circuit then sent the signal to the motors, and we also had to do the optical sensors. And finally, we had to make the shell for the Micromouse. So I'm going to go through each step with you today and how you can do it as well. So let's start with the flood fill algorithm. So over here, I have a little maze set up on the side, and I also have each wall value set. So this side, any wall that is behind the mouse on this side, north, is equal to 4. Any wall side that's west is equal to 2, south is 1, and 8 is east. So you can see that if this wall is what we're looking at, it's going to be 8, because it's east. If we're looking at this wall, from here, from this block, it's going to be 2, because that's west. So each wall is assigned a value. So let's say, for example, we start off in the maze. We want to start off in the first tile at 1, 1. So our maze here is only 8 by 8. So our center is at 4, 4, 5, 4, 5, 5, and 5, 4. But in the actual competition and in the actual maze itself, you want 16 by 16. So it's much bigger. It's double the size of this. So we want to start in 1, 1. Now you can see that we have a wall here, and a wall here. And we're starting in this spot. So that means we're looking at 2, 4, and 8. 2, 4, and 8 all added up equal 14. So we put 14 there. Then the mouse will move there because it's a random guesser, but there's nowhere else for it to go yet. So then it goes here. We have a wall here and here. So that's 2 and 1, so we have a value of 3. Then we move it here, because it still is a random guesser, however, it still doesn't have anywhere to go. The flood fill is really actually just a random guesser that's combining this technique of kind of mapping out where it's at with a random guesser. So then the mouse goes here. We only have a wall here, so that's 8. And from there, it'll keep on going through the maze. So you get back down here, it's 3. You go here, it's 1, and so on and so forth. Now, the other important thing we want to be able to do with this flood fill algorithm is we want it to be able to give back the coordinates of where it's at. So in the maze, for example, if it goes down 1 unit, we want to use a loop to be able to say, okay, if goes forward, add to the y direction. If it turns and then continues to go forward, add to the x direction. So in this case, we start with 14, so we have 1, 1. Then it goes down, so we go from 1, 1 to 1, 2. But then it turns. So then, now instead of adding to this direction, we want to add to the horizontal direction. So now we are going from 1, 2 to 2, 2. And this will continue on. And each time that you do this, you'll set this value of the walls to that coordinate in space. So 1, 1 is 14. 1, 2 is 3, 2, 2 is 8, 2, 3 is 3, and so on and so forth. And by doing this, you're able to not only tell where the mouse is in the maze, but you're also able to go back and say, okay, there are these walls here, because you know that 2 and 1 are going to values that add up for 3 in this case. The last important thing we want to do with the flood fill algorithm in this case is we want it to be able to block off dead ends so that the mouse doesn't go back that way when it's traveling through the maze. So for example, let's say the mouse goes this way. It follows this path and it gets up to here. Now, it can detect that this is 4, 8, and 1. It's a dead end. There's nowhere else for it to go. That's 13. Now, what we want it to do is we want it to turn around and to go back where it came from so that it can choose a different path to go. So what it'll essentially do is it'll go to this space, but instead of marking this as 4 and 2 as 6, it'll block this off because it knows that's a dead end from the walls that we had. It'll block that off and count it as 2, 4, and 8, so it's 14. And then it'll continue to go through this process because now it knows that's a dead end, so it wants it to go back to where it came from. So it'll continue to do this until it notices that there's no more openings. It's kind of like the dog game that you play at a restaurant or a diner, where you keep going until you can't make any more blocks for yourself. So that's really the premise of what we want to do with the flood fill. So by doing that, we're able to block that off and keep going down the path until we can get to the center. Next I'm going to talk about the hardware component of the mouse. So now that we have completed our flood fill algorithm, it's time to look at the actual hardware of the device itself. So what we have here is I have drawn out each of the different types of devices that we'll be using. So let's start with the actual wiring of the H-bridge to the microbit pins. So we have certain pins that are available on the Micromouse, or the microbit, and the pins that we'll be using for the wiring of the motors is pin 15 and pin 16. So to start us off, this is the MPQ22222. What we'll use this for is as transistors for our wiring for the motors to the H-bridge so that we are able to control the speed better of that. So you can see here that there are 4 different transistors set up inside. Next, we have our H-bridge circuit, which is the L293D. So you can see we have enable 1, input 1, output 2, input 2, input 4, output 3, input 3, and enable 2. So we'll be using enable 1 and enable 2 to activate the motors, but we'll be using each individual input to control the speeds. So as you can see here, this is a schematic diagram of each of our pin 15 and pin 16 being used, wiring it to the microbit. So pin 15 is going directly to input 3. However, to control the speeds better, we also have pin 15 going to a resistor down here, which is going into the base of one of the transistors for MPQ2222. We also have a voltage source of 3.3 volts connected to a resistor coming into the collector, and then it goes to ground to the base. Now you can see we set up our input here because the voltage going toward the input is going to change depending on what the input from pin 15 is. So you can see that it's going to input 3 for 15, and then it's coming from the transistor for input 14 here. We also have a similar setup for pin 16, where it's going to input 1 here, and then down here it's going to the base of the transistor, and then you have the voltage source and you have input 2 there. So 2 very similar setups, and I also have a video that I will be showing shortly after I explain the rest of this, showing the actual working of the Micromouse with the correct wiring and the film of it, stopping with the sensors. So moving on to the sensors wiring. So for our microbit, for our Micromouse, we used a phototransistor and an IR LED. Now a phototransistor works very similarly to a regular transistor. However, instead of a typical voltage supply going to the base, we have a light. We have light coming into the base. And pretty much the phototransistor uses the photoelectric effect to convert the light into voltage. So what's happening here is that you still have the transistor, you still have voltage coming into the base. However, instead of just a voltage supply being attached, you have light coming in. So light is going to vary the voltage that you have coming out through pin 0. So in this case, for the phototransistor, we are using pin 0 to pick up or read what is coming out of the phototransistor. So we still have 3.3 volts, we still have the resistor across, and we still have the emitter going to ground. For the IR LED, that's very simply just a voltage source with a resistor across it going toward the IR LED. So that's emitting infrared from it, and it's going to ground. And the way that we have this set up is that we will have the IR LED and the phototransistor right next to each other. So the one will act as emitting the infrared rays. The rays will go, they will reflect off of the object in front of it or to the side, depending on which sensor we're talking about, and it will reflect and come back to the phototransistor. And from that value that we get back, it'll tell us how strong the pulse is that's coming back, which is going to give us different values each time depending on how far away it is. So that's how we're able to tell how far away an object is, by determining the voltage that we get back through pin 0 from sending out the pulse from the IR LED. So now I'm going to show you kind of just a little film of what we had after we set all of this up. Okay, so now we move on to the shell portion of our little talk here today. So what you're seeing is the bare basic shell that I created in 3D AutoCAD. So for this course, we learned how to use regular 2D AutoCAD and 3D AutoCAD, and then we were able to draft our own shell for this. So as you can see, from the front, there's the 2 holes for the IR LED and the phototransistor. And then on the side, we have the 2 holes for the side to detect the walls. So we have 1 sensor in the front and 2 sensors on each side. Just kind of showing you more, this is from the other side. So you can kind of see, I'm not sure if you can see it in the video, but we have the sensors coming in at an angle. So pretty much what we did for that was we wanted to see what the best absorption would be for the IR LEDs. So we figured out that if we set them at angles toward each other, we would get the best absorption of the IR LED, and we would therefore get the best values back on the side. So the front we kept straight, and on either side we turned them in. And then this is a view from the back, so you can see that it's hollow on the inside because that's where all the wiring and everything else goes, like the micro bit. And you can see that's where you would put the IR LEDs into. That's just a bottom view. These are mostly just different angles showing you kind of where each thing is at and how each thing kind of falls into one another. And then this is a view from the back. So you can see where each of the sensors openings would be and how it opens in the back and what it would look like from the front. So, and that's it. So I want to thank you so much for your time, for taking the time to watch my video. If you have any questions or comments, please leave them in the comments below. And then until next time, thank you so much, and I'm Ellie Rosenthal.